So, Osvaldo, Junpeng, and I were writing a book, and here's actually where it is an overleaf. It takes a little bit to compile, but let me give you that sneak peek I promised. Slow start. All right, we'll let that go for a second. Let me set up this other notebook real quick. Chapter 2. Exercises. Still compiling. All right. No big deal. Let's do the imports. It's easy. Still compiling. All right. While that compiles, we're just gonna install stuff. Let me actually stop here and talk about what we're gonna do, in case someone's watching this later. So basically, the big news is writing a book on Bayesian methods, and if it ever compiles, I'll show you what it is. But let's see, rename. All right, here we go, finally. Osvaldo and the rest of us are writing this book, Bayesian Modeling, Computation in Python, and it is pretty meaty. It's got a lot. It's been taking us a while to write, but we've got almost like 11 chapters here. I think 12 chapters of pretty good stuff. How to use computational methods to make estimations of parameters and all that stuff in the real world. And the challenge I've got is I need to make you all some really good exercises. Because, as someone who's pretty adamant about open source and learning and all that, you really learn more when you are trying things out and doing them yourself. And that's really what we want to strive for. So I need to write exercises for this linear regression chapter. And we've got lots of examples of regressions, and we use the Penguin data set, the Palmer Penguin data set. But I'm trying to figure out one that'll be interesting that isn't the Palmer Penguin data set. And so I've got an idea. The idea is, let's see, let me write this down. So you know the problem. Problem is, I need interesting data sets to create exercises with, but I don't want to use the same data sets that everyone else has. I want a new one. So what I'm going to try and do here is I'm going to try and parse a space-eccentrics data set. And I think, my hypothesis, I think I can get 2 exercises out of this. I think I can get a regression example. I should say a continuous linear. Actually, let's call it a categorical or continuous regression of number of Starlink satellites. And I think I can do that. I should be able to sell satellites, right? I worked at the company. And I think we can do a logistic regression of landing success. And that's what I really want to go for. I want to go for a data set that helps to get sort of these two concepts, because from here we can break it down into, I can break this into exercises that show prior selection, model architecture, data understanding, and results validation. And that's what I really want to get for you folks. So let's see. Anyone else joining? I think not. Let me post the link on Twitter just real quick, just in case so people can see. Copy. Okay, so that's what my hypothesis is. What we're going to need to do is I need to get the data from a publicly compiled data set. I'm going to need to do a little bit of EDA. Although less so, because to be quite honest, I'm pretty familiar with what SpaceX does, having worked there. And I'm gonna need to see if models work out for students. Well, I should say for book readers. I want to be sure that the models are useful for you folks, and they don't have any pathologies or challenges or annoyances that would make it difficult to learn the central concept and more just data problems. So there is this awesome GitHub repo that actually, when I was at SpaceX, we were quite impressed with. There's these folks that have nothing to do with SpaceX, but have basically compiled really detailed information about each one of the launches and the Starlink satellites. I haven't used this in a year or so, so I don't know. I haven't seen exactly if anything's changed in it, but in the V4 API. But I don't know. Let's just dig in. The first thing I'm gonna do, actually, is I'm gonna pip install requests. Actually, let me see if we already have requests. Import requests. Yes, we already got it. All right. So what I want to do is I want to get all the landings for SpaceX. So let's say let's just do this on network. Data pulls for landings. And what we want to get here is all SpaceX missions, and whether the first stage was recovered or not. So for the folks that are maybe don't know a lot of SpaceX or are interested in SpaceX, SpaceX recovers multiple parts of the vehicle now. It covers the first stage, but also the fairings. I don't really care about the fairings, which are the pieces that hold the satellite. We just care about this booster here and see whether we can get the booster. So, do I want to use one of the clients? Nah, I'd rather not. I'll just use the REST API. I don't have to use a package. So let's read the docs, shall we? What do we got? So course, crew. Detailed info for course. Actually, we don't want the course. We want launches. Because, just so you know, cores can get reused over and over again. And I really just want to model launches. So let us get the previous launches. Let's just take a look-see here in a good old browser. And what do we got? This. Yes, okay. This looks good. I know there's around over 100 launches now, which is what we want. What do we want to see? We want to see... Hopefully they make this easy for me. Details? No. Fairings? No. Payloads? No. Failures? Cores? Alright. Alright, this is what we want. Perfect. What we want is we want to get all of the launches. We're going to parse through. We're going to see whether there was a landing success or not per year. So let's do that. Yeah, all right, great. Let's go for it. So import requests. I'll say data equals request.get SpaceX launches passed. Hey, somebody joined the chat. Feel free to introduce yourself. Interesting. 2 concurrent viewers. Feel free to say something, ask questions. I should say, I should point this out. Oh, I forgot this portion. I'll say rules. Feel free to ask questions whenever. I'm happy to talk. And then, oh, hey, Neil. How you doing, Neil? And then be nice. We're generally want to be friendly. All right, so since Neil's here, I'll do another quick explainer. For those who don't know, Neil has got a PhD in stats, so I'm gonna talk at a higher level here. But I basically need a data set that sort of models a logistic regression. I didn't want to use one of the pre-canned boring database, or boring data set that's already been used before. So I'm gonna grab the data for SpaceX's first stage landing over time, and whether they landed the vehicle or not, and do a logistic regression using that. So let's see. ABD. I don't know what that is. What's ABD, Neil? You gotta tell me. I gotta learn. Now that you're here, I feel like the stakes have gotten higher. All right, data, and I need data.json. Perfect. So got our data for all the SpaceX landings. I think what I want to get is I want to get a data set. Say data schema. I want to get the flight number. I also want the mission name, because I actually know the mission names pretty well, so and they're kind of fun. So I want the name. I'll put dissertation. Oh wait. I want. Okay, this is where it gets tricky, because some of the missions have more than one core. So for every core, I want landing success or not. This is a one-to-many. You know, everywhere in the world, when you think things are going to be easy, data always screws you up. So SpaceX had the same problem. We used to be one-to-one, right? One core, one rocket, but then they made Falcon Heavy, and now there's 3 cores to 1 rocket. So that breaks all of our assumptions. Thanks, Elon. It was real fun to work with when I worked at SpaceX. Okay, so I want to get that, and I also want to get the vehicle type, because I only want to model. Yeah, I do. I want to get vehicle type because I only want to model the Falcon 9 launches, not the Falcon 1 launches. So Falcon 1 was the smaller rocket SpaceX initially launched, 5 of them, but they quickly moved on to the Falcon 9, which is the workhorse rocket that you see today. I don't see vehicle type in here, which is really troubling. Come on. All right, I think for now, let's just skip vehicle type because I really don't see it. I can try and find it real quick. Falcon. I'll try and type F9. Does that give me something? I'm trying all the words here. Let's try Falcon. It doesn't look like I got it. I might have to manually filter it, which is going to be really annoying. So, all right, forget it. We're just going to do all the rockets. Great. So let's just scroll up here to the top. Let's do this again. Let's just make this 2, so it's smaller. All right. So basically, we need. I'm going to use an. How do I do this? Okay. Columns. Let's just write them out. They're going to be. Flight number, flight name, actually just do name, do core number, just so we know. Let's do launch date, actually, we want that. We want launch date, and let's just go with that. Launch date, and we want landing success. All right. So with this should be pretty easy for loop. So we say for flight in, what do I call this flights? Launch. I'll call this launches. Yeah, I'll just call this launches. Okay. For launch, in launches, we're gonna do flight number equals flight and flight number. Oh, I should have looked at the keys. All right. We can do that. Actually, we'll do a single little core. Single sign here, name. Actually, you know what we'll do? We'll just do calls. Flight number. Oh, but it's a JSON. No, I can't do multi-indexing. All right, well, let's do it this way. Flight name, launch date, and then we'll say cores equals flight cores, and then for core in cores, we're gonna want to iterate here. And get so we'll say data equals an empty list. I'm going to say enumerate cores because I'm going to want to give them numbers. And I'll do I, which means we also need 2 more columns here. We're going to need core number, landing success, and I think we're going to be good. All right. So we'll get name here, and we'll get launch date there. not? And for now, let's just, for debugging, let's just say print core. We'll do, oh, something's off. There we go. We'll do print. Let's see the first 5 launches. All right, so what we're shooting for is just to see whether we break on any keys. And there we go. We already have our first challenge. Okay, so the reason is because we want to iterate through the JSON. We don't want to iterate through the returned object. So I need to say launches JSON equals launches.json. Just throw that in. Launches.json not defined. All right, let's do another query. Flight not defined. Yeah, because I need to change the name to launch. And launch date. All right, this is an interesting one. Why can't it get a key? Oh, all right, so the key must be called something else. So we are looking for date. Date UTC, it's not called launch date. All right. The font is tiny. Thanks, Neil. I appreciate that feedback. Let's just make this bigger. Hopefully 150. Makes it easier to read. Let me look. Yeah. All right. Looks a little bit better. Welcome somebody else. Oh, and they dropped off. Okay. Neil, I'm surprised you want to watch this. Okay. Flight. All right. Cool. This is close to what we wanted. Here we go. We got the index. We got this. We got the date. And we're getting a core. So what we want to get from the core is we want to get core dash the reuse. So in the core objects, I want to get, actually I want to get landing success. That is what I want. That is what I want. And I probably should get landing attempt too. I think those would be good things to get. All right, print. Landing attempt not defined. Oh, it's because it's there. All right. And then let's just actually just try 100 of these. And this is looking pretty good, actually. This is what I'm going for. All right, cool. So that gets us our data. So for those who just joined, we're trying to parse the SpaceX dataset to grab a public SpaceX dataset to grab information on the number of launches and whether stage recovery was useful or not. And the idea is, I think this is going to help. This should be nice for one of the logistic regression examples that we're working on. So let us add this and make this a data frame. So data scientists love tidy data. We just love tidy data. So let us make this tidy. So what I need to do is I need to say data.append, and I'm just going to do this lazily. Flight number, name, launch date, core landing, and what I want at the end is I want a data frame. df equals pd data frame of the data and the columns. So we say columns equals columns, and let's see if this actually works. I will be surprised if it does. Oh, and I can take these print statements out. But it seems to have worked, so that was surprisingly easy. I'm flabbergasted because it usually does not turn out to be that easy. Let's look at the last couple flights. All right. We're looking pretty solid here. Let's update these columns, make these a little easier. And I definitely then broke something. What did I do? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And what do I got here? 1, 2, 3. Oh, core number. That's what I need. Core, good old core number. Is out of sequence. So, flight number looks good. Name looks good. Core number's in here twice. That was not what I wanted. Flight number, name. Move launch date over here. Core number. Oh, and I don't want landing success twice. I want landing attempt. So landing attempt. I should probably make these consistent. Flight number, launch date, core number, landing attempt, landing. Landing attempt. All right, so what are we? All right, that's not as easy as I thought. I should not have spoken so fast. Flight number, name, launch date. Flight number, name, launch date. Core number. Why is launch date not showing up? Because I need to refresh my variables. All right, classic me. So I was using an old list. All right, great. So we have got everything, and actually, for good measure, let's actually just plot this. This might be interesting to plot because this will tell us whether it's going to be a good problem or not. So we'll do EDA plot. And so I see a bunch of people just joined. I wanted to say, feel free to ask whatever questions you want anytime. I don't mind. Well, let's make an exploratory data analysis plot. I think I need to make sure that the this is a date. So let's do df.dtypes. And it is not. So let's just do some quick data cleaning here. Yeah. Just launch date equals pd.to date time. Data frame launch date. That should set it as a date. I think I should be able to do then. Let's see if this works. df.plot kind equals scatter x equals launch date y equals landing success. All right. Oh man, that looks pretty good. I mean, we're getting there. So admittedly, I'm checking my knowledge because I've done this before, and some things I want to change. Looks like there are some failures down here, which is fine. But I want to see some more of the launches back here. And I think what's happening is, let me explain this. The first launches SpaceX did where there was no landing attempt. Oh, landing success. Landing success was none. It's not a Boolean. It's I actually don't know what this is. Probably just a string. So I need to replace these with a false. So that's what I want to do. All right, so we're gonna add another column. We're gonna say landing success. This is landing success. We're gonna make a binary landing success. So we're gonna say df landing success binary equals we're gonna landing success got replace, and what we're gonna want to replace is, I think it's a none string, so because it's JSON, and we're gonna want to replace this with false. So what we're saying here is what's represented in the data, the raw data, is that if there wasn't a landing attempt, the landing success is none, which is, I guess, is true, because there's actually 3 states where they tried to make a landing and it didn't work. The rocket couldn't land at all, so it didn't matter, or they tried to make a landing and it did work. And we want to take that tertiary space and turn it into a binary space, because I think it's going to make for better problems. So let's try this and let's see what happened. And it did not work. So data frames and data types are annoying. So what we're going to do, we're just going to do this the cheap way. We're going to grab the first index, the first row, and landing success. Try to get it that way. All right, perfect. So now we got landing success binary, which means when we plot this, we should see more dots over here on the left, because now we're including all missions, even the ones that previously had none. And what do we got? Did not work. Why did it not work? Let me try that again. Here. No, that's the old one. Why do we get it here? No, that is right there. So I am confused. So the data frame is telling me that it doesn't have this particular column. I don't know why, because there it is right there. All right, well, if I can't do it through pandas, we're gonna do it the old-fashioned matplotlib way. So let's just comment this out. I don't want this noise here. Pretty big fan of the object-oriented API. So plt.subplots, ax.scatter, df.launch date, and then df. Gotta do the import. Import matplot lib.pyplot as plt. Grab the plot, and then let us. Perfect. All right, here's what we wanted. All right, folks. So what we want to do is what we want. Actually, let me add some more titles for you. This is whether SpaceX launched a rocket and whether the landing, the first stage only landed or not. And what we have here at the bottom is that it didn't land. That is 0. And what we have at the top is it did land, which is the success case. So that is the plot that we want. So add a title. That's a title. Landing success. All right. So awesome. That was quicker than I thought it would be. That only took, 40 minutes. So actually that was longer than I thought it'd be. But all right, we are good here. Now I think this is the data set that I want to use to make a logistic regression. So let's just do that. I'm gonna cheat and I'm gonna copy one that I already have, because it's way easier to copy one that I already have. If anyone watching wants me to talk through the API of PyMC3, you just let me know, and I will be more than happy to do so. But if not, I will just copy it over. All right, so what do we got? Here it is. So I'm copying the logistic regression from the book. I'll go through it real quick because it might be fun. So for those who don't know, logistic regression is a generalized linear model that lets you model anything, but in this case probabilities. It's really good at modeling probabilities because it constrains the input, or the domain. Constrains the response to between 0 and 1, which is just all good for probability stuff. And what we're doing here is we're using PyMC3 and good old Bayesian stats to estimate the many parameters, the 4 parameters, I think, the one we're doing. And we end up getting a plot like this. So we're going to do the same thing, but for the SpaceX example. So I've already got most of it set up here. There's the model context for PyMC3. We got some hyperparameters and some priors back here on what they are, and then we just keep on going. I gotta be honest, if we were doing this for real, I should probably do some prior predictive analyses and things like that, but I'm just gonna wing it for now. We'll just so they feed into the back end and work. So let us do that. So I have a little bit more data cleaning to do. So let's do it down here. Let's get our x-axis. That's what I'm trying to say. Okay, so I'm gonna say I'm gonna call this relative date. Well, we'll call it relative date in a second. So relative date is gonna be what we're gonna call it relative day. Relative launch day. What this is going to be is the launch date of the vehicle relative to the first launch. So the first launch was RatSat, or FalconSat, I should say. And what I want to do is I want to shift these. Actually, I just want to get the days out of this. So I want to do launch date minus launch date min, and I want to get the days out of this. So .dt.day. Ooh, doesn't have days. Great. Okay, great. So what we have is we have the relative date of when each rocket was launched. The first one was launched on the 0th date, and then the 105th launch, which just occurred last week, I think, is on the 5,260th date, which sort of checks out because it's been about 13 years. And if I'm doing the math right in my head, 13, 14. Actually, how many years it's been? It's been about that many years since SpaceX launched their first satellite. Oh, actually, first one was in 2005, so 15 years. Okay, that checks out. So this is the one. This is like a couple weeks ago, because if you take 15 years ago and add 5,000 days, it's about last week. So last week or so. So we're gonna call this relative launch day to get an x-axis that's an integer. Get an x-axis. It's an integer. All right, so we're good there. And I think Theta will handle the Boolean date type of the y-axis pretty readily. But we can double, just to show you, df dot landing success binary. So this is a Boolean right here. So I think everything's just gonna work out just nice. So what we need to do this logistic regression is we need to model the mean, and I'll pause for like 10 seconds, see if anyone's got a question about logistic regressions, because I'm happy to explain them, but if not, I'm just gonna barrel on through. But actually, let me explain one thing, because we're here. What I would do in this other logistic regression, because it might be interesting, is we were trying to see if we could figure out the species of a penguin by their bill length. This is the Palmer Penguins data set from Catherine Gorman, which was pretty handy. It we're trying to get away from the IRA stuff because, you know, Ronald Fisher was, I guess, kind of a jerk in a couple ways, and we want to support other people. So Palmer penguins it is. We were predicting the species of a penguin using their bill length, and you can, in this case, you can see it turned out pretty nice. You can pretty readily tell the difference between an Adelie, or a chinstrap penguin based on the bill length. So if you ever find yourself one of these days with a penguin that you're sure is either an Adelie or a Gen 2, you don't know, measure its bill length, and if it's over around 45, it's a Gen 2, and if it's below 45, it's an Adelie. Now you know. We're gonna do the same thing with rockets, but what we're gonna do is we're gonna see whether SpaceX got more successful landing its vehicles based on the day. So we'll do relative launch day here, dot values, and then we have our beta 1 parameter. This is the sigmoid function, which takes this linear function and squashes it into the 0-1 bounds of the response, and then this is actually the calculation for decision boundary in a univariate logistic regression. So this kind of tells you when things shift from one class to another, and I think that's all we need. So let's just try it. Let's just go for it. Let's just see if it works. I don't have a prior. Well, should I? I should do a prior predictive analysis, but you know, we're just gonna skip it. We'll just skip it to make things fun. We're not doing penguins anymore. We're doing rocket landings, which is way more interesting. Hopefully no one is a penguin scientist in here. And quick fun fact about PyMC3, let's do a pitch here. PyMC3 has a trace object, which was the old thing, but now Arby's has got this inference data object, which you're going to see here in a second, which is quite nice. Dang, and we already got an error. All right, why? Because I didn't run that. All right, so we are going to run our MCMC sampler here. So turns out, for those who don't know, Bayesian statistics is pretty cool math-wise, but it's pretty cool when you write it down in symbols, but it's kind of a pain in the ass to solve on paper, except for certain models. So recently, folks have come up with these algorithms that make them easier to use. You don't have to worry about your models as much. You don't have to worry about your models as much because this fancy MCMC algorithm will sort of just like magically get the posterior for you. Now, it's not always guaranteed, and there's challenges, and you're seeing the challenges here in real time because I'm getting some problems here. But my first problem is I screwed up on the programming. So I need to fix the name there. Let's sample again, and let's figure out what I am doing wrong. Okay, so this is the challenge with MCMC stuff is ideally it just works and everything. You get your samples and life's just great, but that's not always what happens, as you can see right now. Samplers, as the name sort of implies, they try and sample from the posterior and figure out what the posterior is, but the posterior geometry can be challenging. You can misspecify a model, like all sorts of things can go wrong. And what that means is that even though I pulled, in this case, 12,000 samples, PyMC3 is telling me that a bunch of them were not useful, 75% of them, and that is a pretty good indication that something is messed up about my model, potentially. And so with samplers, you spend a lot of time looking at diagnostics, and that's what we're going to do here. We are going to figure out what the deal is. So what we're seeing here is various diagnostics for the plots. I don't want theta. Theta is not going to be very useful, so I'm actually going to subset this to to beta 1, beta 2, and beta 1 and beta 2. Let me explain what's going on. So the what we're getting both the trace plot and what's called the kernel density estimate of the posterior of the parameters. So this tells you what your sampler is doing. This tells you the results of your sampler. But you also get samples for every single rocket launch. There's a theta estimated for every single rocket launch, which is why you see like 100 colors here, because there's 105 rocket launches. I'm not so interested in the particular probability for each individual launch. I'm more interested in what's going on with my 2 sample parameters. So let me filter the variables just to the parameters just to the ones that I want. So those are these here. And so I'm a little confused because it actually looks pretty okay. Like these traces look okay. But I want to know my sampler says something's wrong. So let me see what is going on. So I'm going to use ESS. And, well, that didn't help. I want to get let's do dot summary. Okay. And I want to get the numerical diagnostics. So to give you a sense, usually my workflow is I look at the visual diagnostics first and see if there's anything wrong. These visual diagnostics actually look pretty okay, so there's not much I can learn from them. But let me grab these ones. So what I'm getting here is I'm getting parameter estimates. My beta 1 parameter, okay, this might be why. My beta 1 parameter basically has like no mass to it. There's basically no slope. It's saying nothing is different, which is pretty weird. I would have thought that things would have changed over time. This is giving me an estimate of whether my notation is backwards. So Neil's pointing out my notation could be backwards, which could be true, and that's one thing that could screw things up. The only reason I don't think my notation is backwards is because I ran it. Well, this is why I call it copying models. Is I ran this one and I copied the same notation and it all worked out. So I feel like the same thing should happen here. The slope is per day. Yeah. Okay. Neil points out the slope is per day, which means it's super small. But what we can do is let's just plot it and see what the hell it looks like. That's kind of what I do. That's a good point, Neil. This is why I probably should have gotten a PhD in statistics, so I could have been as smart as Neil here. All right. Let's just grab. Let's do everything with the decision boundary first. Let's do the easy stuff. Steer between scatter. And in Neil's point, maybe I might switch this from days to launch number, because that actually might make things core number, because that might make things easier. But we'll do that in a second. Let's just try this first. Let's just copy some of this stuff over. These labels are going to be wrong, but let's just try it. Cannot reshape array. Oh man, so you guys are going to watch me do my favorite thing, which is array reshaping. The good news is, again, things are copied and pasted. Not so bad. Okay, this is going to be fun. So another fun fact of life is you spend a lot of time reshaping arrays to make stuff work out in in data science life. So what I want to get, let's get this right. I want to get the mean of every estimate of theta, although I'm trying to think. What am I using it for? Let's actually just leave it for now. Let's see what we get. That's not a great plot. Okay. All right, we want the scatter plot first. Let's just do that. That's the easiest one. Let's just build this up one portion at a time. Decision boundary last, and we'll get the HVD plot last. All right, I have to import NumPy. Should have done that at the beginning. Color keyword. All right. What is happening is I'm just trying to plot the results now as a graph, and I'm trying to recreate this particular plot. This one down here. So this is the one that we have for the penguin regression that I already had a problem, and there's actually numerous things here. There's a scatter, which is the observed data points. We actually already have that one, so I might go and use that one. What I'm really interested in at first is this mean line, and this is the logistic regression over time. So let me get that going first. So the scatter, I'll just let me just copy from over here, just so we don't have to spend a lot of time on it. And let's just make sure that works. Should. Okay, great. So we have the scatter plot. The next is we want to get the mean estimate of theta for each one of the each one of the estimates. So I want to double check what I had it over here for. So I got the posterior, got the theta parameter, and then what we plotted was for every index, we got the theta, got the bill length, and we but this is a little bit different. This is not a time series problem. This is a scatter plot. So this is actually subtly different. How do I want to do this one? So on the SpaceX problem, I was using days, but it actually should just still work out. I was using days. This one uses bill length. So let me think through this really quick. We sort the index, so matplotlib acts nicely. I don't think we have to do that for ours, but we plot. Okay, we plot the days and plot the data. This should still work out. So I need to reshape this array. And reshaping is something that I always fumble over a ton. So we have two chains, 5,000 draws per chain, and we have 106 estimates. That's one for each of the launches. And what I need to do is I actually need to, so I need to collapse these two and then take the mean, which gives me the probability per launch. So I think actually I should just be able to do it with -1. Let's try this. Reshape. No, that does not do it. I think, well, this didn't work, but let's try it here. Reshape. Okay, that worked. Okay, so that's what we want. We got 10,000 samples for every single rocket because 2 chains of 5,000 draws is 10,000. And we want the mean at each one of these. Whoops. Okay, perfect. So this gives us an array for each rocket launch. The estimated theta probability of that vehicle's core landing. So we should be able to get that here. So, all right, great. Theta worked. I don't think we need the arc sort because things are already sorted by time. So what I want to plot in this case is, let's do time first. I want to plot the our x-axis, which is the relative launch day values, and our theta, and fingers crossed. See what this looks like. Okay, fun data science thing. It starts at 1970 because that's when Unix epoch time starts, and we need to set the offset of the min launch day. So what I need to do is I need to add back in the minimum date. So let's just do this. Let's see if I can do this the easy way. Plus, actually, dot min date dot min. Nope, I want launch date. Always having fun with the column names. I gotta say, datetime handling is definitely not one of my favorite things to do. So we need to get days from epoch start. So let me find it. Python. Well, hold on. Let me think through this. It's nice that they converted this into days, but it's not exactly what I want. Maybe I'll just stick with relative launch day, and we'll just go with it. Well, actually, I'm surprised because when I plot this, oh, I know why. Because this is setting the axis. Okay, so I don't want. Let me do this. So what's happening here is matplotlib is getting two types of axes. It's getting a date from here, and it's getting an integer from here. But we just want one. So let's just change the relative launch day. We'll start it at 0, and then we'll plot. And actually, this doesn't look too bad. I am not too bad. Hey, Taylor. Yeah, you joined in right with the fun of it. Okay, this is actually pretty awesome. We are getting a pretty good estimate. I don't know if it's a good estimate. I shouldn't say that offhand, but we're getting something pretty good here. So what we have is every SpaceX launch attempt and whether the core was reused or not, or sorry, the core was landed or not. And at the beginning, it was not, and then over time, it turns out it was. I'm pretty psyched. So unfortunately, the x-axis is a little. It's not wonky, but it's in relative days from first launch, which is like not all that interesting. We'll probably want to change this to date at a future point, but I'm gonna leave that. I'm gonna leave that be for now. What I'm actually gonna do is Neil brought up a pretty good suggestion. The beta estimate parameter is pretty small. It's actually really small because we're modeling over a really big time scale, and so let's just change this to the core number, and that way it's a much smaller axis between 0 and 106 rather than 0 and 5,000. So I'm gonna copy this same regression, and I'm gonna bring it again. I'm also gonna do this because I'm gonna hope that it might make my sampling work out a little bit better. I had some sampling issues here, and while I could dig into them and do some tuning, I really don't want to do that much work for an example problem. And I actually don't want the people who are learning from the book to do that either, because you know, I want this to be easy for them and not a pain. So let's do Logistic Regression, core number versus success. So we just need to change this to, I think it's called this core number. Okay, well, here's a fun one. I clearly made a mistake here. I don't want these core numbers to be 0, so I need to change my data set. All right, so I need to go back here. I'm going to say, okay, so here's what's happening. I have the core number is relative to the rocket, so I need to change this to vehicle core number. And to give people the sort of the SpaceX understanding, most of the SpaceX rockets, I think you guys have seen them, but let me show you. SpaceX. Most of the rockets are single core, like this. Actually, seriously, are single core as they're called. Come on. Why does this picture not want to come up? Let's click view image. Oh, these are tiny. Okay, they finally came up. Most of them are single core, like the Falcon 9 right here. But just because, you know, once you set up all your schemas in your databases to be 1-to-1, Elon likes to change the architecture of the rocket like 5 years in and make a Falcon Heavy, which is 1-to-many. So this is Falcon Heavy. This was a test launch, and this has 3 cores. So there's like core 1, 2, 3 for different launches, and then there's also 3 cores for one launch. So we need 2 numbers. So vehicle core number will be this one. We'll call this one vehicle core number. And I'm gonna be a little sloppy here with my Python, but the capitalization. But we're also gonna call this the I'm gonna call this the launch core number. Equals yeah, we'll start with 1. And then what we'll do is we'll do launch core number plus equals 1. We'll add launch core number here. We're gonna add launch core number there. And then we need launch core number here. And then we're gonna run this. And we're gonna get an error, of course. And that's because I should name my variables the same thing, clearly. And then I get another one because I need to rerun this, of course. All right, but now we are good. Sort of. That did not work. Launch core number. Well, why did that not want to work? So what I'm looking for is the launch core number to go up, and it definitely did not do that. Oh, because it's in the loop. That was also dumb. Okay, so let me move it out of loop. All right, here's what we got. And let's start vehicle core number at 1. So, all right, perfect. Here's what we want. We want the number of cores increasing. We want the vehicle core number, just in case, but now we're gonna go down here and we're gonna change our logistic regression. We're gonna change it from we're gonna change the x-axis from being a date to being the launch core number, and we want this to be the landing success. So I'm gonna run this model again. Again, you know, you should do prior sensitivity analyses and things like that, but we're not gonna do that. Okay, that's because I'm missing another key. So this is the one thing about notebooks. You end up with a lot of cells that you rerun. So I need to fix that there. And I need to fix that there, probably. All right, I think we're good. Yes, Neil's got it. I should just pair program with you guys all the time. All right, cool. And this one's looking pretty good. There's like this, there's this folk wisdom with sampling that if your sampling is slow, then your model sucks, or your model is misspecified in some manner. The sampling wasn't slow. We still ended up with some issues on the parameter number, but let us take a look. Easy.plot trace. And then just like before, I just want to grab two of the free variables and not the estimate of the mean, or the estimate of theta, I should say. So I'm gonna grab these two. So I'm in here, and this doesn't look this doesn't look too bad. I wonder why my sample is having issues, but I'm not gonna sweat it for now. For those who are newer to Bayesian stat, Arby's has got this new diagnostics from Aki Veetari, who is an awesome professor at Aalto University in Finland, and he's actually strongly suggesting, he's got a pretty good paper suggesting why we should use these things called rank plots these days rather than trace plots. So just to give you guys a trace plot explanation, if you haven't seen it, this is the walk the MCMC sampler takes in the parameter space, and what you're looking for is that the trace is able to freely go up and move throughout the parameter space without reaching any sort of restrictions. If it was stuck in an area, you'd see like a high area and then a low area, maybe a high area and a low area. But in this case, it looks like it's going up and down fairly well. There's some areas where it seems to struggle, but you get this quote-unquote fuzzy caterpillar. The hard part, though, is this can actually hide a lot of discrepancies, particularly when you run models with like 5 chains. Like maybe one chain is failing, but it's all mixed up in there. Rank plots are an alternative diagnostic that does the same thing. And what they do is they rank the samples. And if a chain gets stuck in a particular region, you'll see that it'll have a lot of, it'll have sort of a non-uniform distribution of these bars. But this one has a pretty uniform distribution of these bars. So it also looks good. So we'll go with it. I'll probably have to come back and explain what's going on here to the students. But for now, we're just going to live with it. So let's get our summary again, because the summary is real interesting. So let's get a summary. All right, and we get a bigger, well, not a bigger, but like a relatively numerically bigger estimate of beta, which is nice because now these numbers are more interpretable. You get a standard deviation estimate of the parameter error and some nice highest density intervals. So let us plot this one and see what this one looks like. And I need to change the x-axis. All right, this is okay. It's interesting. So this one tells a different story. And actually, it's a very interesting story. So I don't know whether I like it or not. But basically this model is telling us that on its SpaceX's first launch, it had a 20% chance of recovering that vehicle because just because of the regression parameters. So this is, as a domain expert, this is kind of absurd because I know that there was a 0% chance. Like SpaceX had nothing figured out about recovery or anything. Like nobody thought that vehicle was going to get recovered at all. Like literally, it was a 0% chance it was going to be recovered. Like through anybody who looked at the rocket and knew anything about rockets. But because we've compressed the space so much, what happens? There's a bias in the parameter space here, in that SpaceX used to launch one rocket a year at a time. So it took a long time to get the first couple rockets up in the air, but then over time it's accelerated its launches. You can get that sense if you look at this plot. There were very few launches; it's very sparse, and now we're just launching or SpaceX is launching like crazy. So the relative density of the launches is like way skewed to the right, but we get rid of that when we go to a core level. So what actually might be interesting is I'm still going to use this as an example, and I'm going to have folks explain why this was a good idea or a bad idea. So one thing we can do is we can set a pretty strong prior where we tell the model that it has to have a steeper slope, and then it'll maybe do the thing that we want to do. But this also just isn't a very good model the way it's set up, so let me debate later whether we're going to do that or not. But This is a neat outcome. I mean, this is a good outcome that I'm probably going to put as an exercise. It's like model the logistic regression both ways, and then explain why this model sucks, or why this model is not so useful to answer the question of whether SpaceX is going to recover a booster or not. And this model is actually much better. Well, from a domain perspective, I can tell this model is much better because there is a pretty good chance SpaceX is going to recover its boosters. Now, what's interesting is so this is the last bit. This may be the last thing I'll try. What's interesting is this is saying there's an 80% chance that SpaceX is going to recover a booster. But what we're also including in here in this data set are boosters that SpaceX meant to blow up. So they're every now and then, we intend to get rid of a rocket, our booster, on purpose because it's we need to or SpaceX needs to for a particular mission where there's no fuel left to get back to shore, or there was like a demo recovery mission where it was blown up on purpose to show what would happen if a booster failed, or it's just at its end of its life cycle and it's okay to do that. Turns out the laws around rocket trash and things like that are kind of weird. Actually, interesting story on this. One time SpaceX meant to destroy a rocket, so we landed it in the water. So what we did was we didn't want to recover it, so we didn't put the drone ship out there, but we still tried to practice the landing. So we practiced the landing on water, and then the rocket landed on the water and then tipped over, and it didn't blow up, which is a big problem actually because it's still like a humongous bomb, and if somebody comes next to it, it could blow up. It's still a rocket that we don't want people stealing or taking, and I don't know if people know this, but countries sometimes try and steal each other's ships from like the bottom of the ocean for trade secrets or to understand what's going on. There's actually a really interesting story about an American recovery of a Soviet sub way back in the day, and Americans had to fake that the recovery was a mining expedition. But yeah, we don't want you don't want anyone kind of taking a classified sort of booster there. So there actually is some form where you can ask the Air Force to come in and do an airstrike on a booster, and that's what we did. We asked the Air Force to go in and bomb one of the rockets. Let me see if I can find that. Let's see. That's what was the rumor. Okay. Well, I guess I was wrong. I will point that out. I had heard that that's what we did, but I guess I was mistaken. That is fake news. So ignore everything I said. That was just a dumb story that had no truth to it. Well, that was that. Okay. Well, yeah. See. Yeah. All right. Guess it was fake. All right. That had nothing to do with modeling. That was just an interesting rumor. yeah. That's Tyler. I'm glad you enjoyed it, Tyler. Okay, cool. So I got what I wanted out of this. I got the logistic regression model. So what else I wanted to do was I wanted to just parse. I need a linear model. I just need a straight linear model. So what I'm going to do is I also want to understand how many Starlink satellites are in space. So for those who don't know, Starlink is a constellation of satellites that are going to provide internet anywhere on the globe, because we're going to cover the whole globe in radio signals that get you internet, and it's actually working. People are using it in Canada and things like that, like beta testers. But what I want to do Bayesian wise is I want to create a linear regression for the number of Starlink satellites that are in space at any point in time. Space at any point in time. And so I need to get from that same data set, from that same API, the Starlink satellite number and when it got into space. So sort of the same thing as before. We're going to use this API that is nothing, again, not compiled by SpaceX, but some volunteers that just put awesome information on the internet. So let's go through the data collection again real quick. This one should be faster as well. Starlink satellite numbers, and let's grab that. So I'm gonna copy and paste a lot of code from before, so you don't have to bore you. This code to help you newcomers out is what gets the information off of this API. So let's do Starlink. Let's call it Starlink payload, which is actually kind of funny because it's a double entendre here. Payload for the internet term and payload for, I guess, the rocket term. So Starlink payload JSON, and then Starlink payload. And let's take a look at what we got. All right, great. We got our Starlink stuff here. Actually curious what the length of this is. And launch date, decay date. Oh, this is interesting. And actually decay date too. Okay, great. So let's actually get a count. I'd expect this to be, I think it should be in thousands now. I sort of lost track, but this should be, yeah, okay, 1,000. So just so you know, SpaceX needs to get like at least, I believe, I mean, it's been a while since I've checked, but I think around 4,000, 5,000 satellites to get pretty good coverage. And then Elon wants to get to like 10,000 satellites, because the more satellites you get up there, the faster the internet will be, and the more people you can put onto it, and the more bandwidth and all sorts of crazy stuff. So let's look at this again. We want to get the number. So I want to get, let's write this down. I want to get the object name. Actually, yes, let's do name, because name's nicer. So we want to get object name. We want to get launch date. And then I guess while we're going through it, let's also just get the decay date. Where was that? Ah, here we go. Okay. And this is kind of interesting. Object structure. It's got this thing, key space track, and then it's got the stuff after it. I don't know why they do that. So let's just write this down. Okay, so I'm going to copy the for loop. I don't want to type all this stuff out again. So let's copy your for loop for back here. Let's paste it down here. And we'll say, we'll call this satellite number. Call it sat number. For sat in, well, I might not need this. We'll find out in a second. Let's just remove it for now. For sat in Starlink payload JSON. We want to get, well, we want to get the object. So just gonna call this object equals Starlink payload JSON dash space track. I don't know whether it's a one-to-one relationship, so let's just I guess let's just write an assert I guess assert type object actually is instance. So what I want to do is I'm going to check this. I want to check this as a dictionary, because if it's a dictionary, then it's not. There's not like multiple satellites under the same space track, and I can just grab the stuff out. And if it is a dictionary, then what we're going to do is we're going to append to data. Let's do this. Calls equals object name, launch date, decay date, and we'll say row equals this. Actually, we can just do a list comprehension. So I'll just do data.append object call for call in columns. Hopefully this just works. We're just gonna find out. List indices must be integers or slices, not string. I need for set. Okay. All right. Assertion error. 7 columns passed. Oh, this actually might work out. All right. Well, that worked. All right. Was not expecting that to go so well. Okay. So what I want to get. Oh, shit. Oh my god. That's what you hate to do. Get a little happy with the deletes. Okay. What I want to do is I want to see how many satellites are in the atmosphere at a point in time. So, or over time. So I'll do. I'm gonna add a cumulative sum index. So I'm gonna say df dot. Well, actually, I have that from the index, so this actually might be pretty easy. So I'll just do df equals df dot reset index, I guess. Or no, I know. I know what I need to do. I need to count by. Let's do a count by date. Df dot group by launch date dot count. That's what I need. Okay. And I really just want the launch date. So actually, I actually just need the series. So launch date dot value counts. And that is, yeah, pretty much what we want. So I forgot if it's sort or sort values. Oh, because it's sorting the values. Duh. Okay. We're gonna make this 2 data frame. Series object has no 2 data frame. Let's do. Can I reset the index? Yeah. Okay, that's what we want. Okay, so that's what we want. Sort values index. All right, one step closer. So we'll say sat count, and then sat count cumulative equals sat count and launch date is actually a bad name, so I should probably rename it. Let me just do that right now. df.rename launch date to num launched. No, sat count. Oh, did I? Okay, wait, okay. In place. Go long, change the launch to +1, decay to -1. Oh yeah, I guess we could do that. Let me do that later, Neil. I want to do the easy thing right now is just figure out how many are launched. Because that'll make it monotonically increasing, which would be nice for linear regression. If I add the dynamic of launches and decays, then as you can tell, then it could become non-monotonic, and things like that. So let's just leave that. Let's just leave that. Let's just leave that out. Make this the boring linear regression problem because this is only chapter 2 in the book, and we'll make things easy. But that is actually an interesting thing. I'm actually going to model that later. I'm actually kind of curious. Okay, so set count. That did not work. Why did it not rename this thing? That is annoying. Well, let's just try this. That also did not work. Okay, this is where, you know, I think you got to do axes equals 0, axes equals 1. All right, yeah, there we go. Always in doubt, just guess parameters. Okay, we got that, and then I want to get the cumulative sum, so sat count dot launch date dot cum sum. I gotta remember how to cumulative sums in pandas. I think it's rolling, but we're gonna find out right here. No, it is cum sum. Okay. But it's only implemented on a data frame. So series cum sum pandas. Okay, it's also implemented on a series, so that should work. Well, let's just try it down here. Oh, maybe because I have a key error because I renamed my column. Who would have thought? Who would have thought? All right. Okay, great. That is exactly what we wanted. And this, again, I'm going to look at this. This actually checks out because we did launch 2 satellites on the first launch. These were the initial prototypes, and I was there at the time. And then we launched 10 as part of a rideshare, and then we launched another one just last week. So great. Great. All right, let's make a plot again just to take a look at the data. X equals, I should rename this from index, but you know what? We'll roll with it. And then we'll name this cumulative. I probably should name that cumulative count. Hopefully this looks linear. Oh my god, perfect. This is exactly what we wanted. It's pretty linear. Although I'm suspicious because it's too linear. And my assumption is that this is not a date. This is a category. So let us make sure that it's a date real quick. You renamed a column still set to launch. Man, okay, so YouTube streaming is a little slow. I guess I get your comments like 30 seconds after on. Come on, YouTube, you gotta step up your game. Make your streams more real time. I'm sorry about that, Tyler. You pointed out my error. That would have been nice had I got that in time. Okay, so I'm actually just gonna rename index as well because index is not a good name. Index, and this actually should be launch date. So we gotta swap these around. So let's just look at this real quick. Okay, we got that. Sat count dot. Oh, wow, how did I do that actually? Sometimes I do things that I don't even know. Sat count dot launch date equals pd dot to date time. Sat count launch date. Okay, this should be a date time now, which means a time. This should be a time object. So now if we change to that, okay, this is a little bit more of what I wanted. Now, this does not make for a very good linear regression problem. So I think what I'm gonna do. Is I'm gonna truncate the data in 2020 forward 20. Let's see. Yeah, I'm gonna truncate the data for 2020, and then we're just gonna ignore this long period of time, just so I can make this linearized to make this a good example problem. But yeah, otherwise it would not be a good estimator if we took the full date range. It also makes sense when I work there, just because we launched some prototypes way back when, And then a lot of stuff happened, I gotta admit, internal at the company, like a bunch of stuff. So there was a pretty long gap when they were doing some stuff. I don't know how much I can talk about it, but just like some stuff, and took a while to kind of get back on track. So you can see once they got back on track and we hit our stride, things turned out to be pretty okay. So let's create an indexer. Sat count, launch date greater than. I think pandas can implicitly do the date-time conversion if I make things ISO format, but let's try it and then we'll see. All right, yeah, look, it worked. Okay, great. So Neil, should I do a log transform? In this chapter, I don't want to do a log transform because this particular chapter. Actually, let me just show you. I still have it open. Let me show you. So this chapter, this is gonna take forever to compile. This book is massive now, so now it's like takes forever in Overleaf to compile. Let me see if I have another copy downloaded. I don't anymore. Okay, we're gonna let this compile. I'll come back to it. But this chapter 2 is just linear regressions. We don't have any transformations on the covariates, just the transformations for the generalized linear model. The transformations come into in chapter 3. Here we go. So chapter 2, let me actually just go to, I don't know, it'll be most interesting. Yeah, chapter 2, you can kind of see it here with the file outline. It just has univariate linear regression, multivariate. I always mess this up. I know we changed the name. Multiple linear regression, because multivariate linear regression is something else. Multiple linear regression, generalized linear models. It's chapter 3 that has the covariate transformations. So I think what I will do is I'm going to make this example. Where did I lose my Overleaf? So I just messed this up. I'm going to make this as an example. I'm going to reuse this example for chapter 3 where we go into, our naming is a little bit off, but chapter 4 where we go into transforms. So here's an example of we did a covariate transform for this, where this became a square root. And we're like, hey, you're going to want to linearize things. Oh, this plot's a little messed up. I got to fix it. But we do the square root stuff that you're talking about. But for now, let's just jump back to this and make this we're just going to cut off the portion that's nonlinear. So we'll say launch filter or date filter. And we'll just filter the dates out, and then we'll be as this linear, and like, yeah, okay, cool. Looks linear enough to me. So what we'll do is we'll do the same that we did in the other with the other model, which is set a relative launch date. Let's just do this. All right, df equals launch date. All right, I called it something else. Oh, sat count. Sat count. And I still have a mirror. Oh, one more. Okay, great. So now we have a date. So we're going to change this to relative launch day. Yeah, it should be fine because we can just say the intercept is meaningless, and then we'll. So what I'm thinking in my head is because it starts at 700, where if you extrapolate this model, particularly closer to 0, It's going to say there's negative satellites in space, which obviously would be kind of dumb. But this will be good too, because then I can throw this in the example and say, what happens to the launch day 0? What is going on? And then, people have to, understand that it's a model and think about that it's a model and understand that it's a model, and that'll be just a really good portion of the exercise. So actually I like that. Okay, cool. So we're going to do the whole Bayesian thing again. This time I'm going to do it from scratch because it's a linear regression. It's not too bad. So we'll do with pm.model as sat model. And then we need, in this chapter I've been doing things, in this chapter we don't have we actually don't show dot product notation, so we're just going to leave that off. We're going to do beta 0 equals pm.normal. And I'm going to set a fairly wide prior. Let's say beta 0. Actually, let's just set a really crappy prior. Let's just say we have no idea. So what we're saying is that we have no idea what our intercept is. Well, we have some idea of what our intercept is. It's centered. It's probably 0 centered, but has a massive standard deviation. And then let's set one for our slope. I'm just gonna say 30. So I know it's 60 per launch. So this fun fact, it's most of the time it's 60 per launch because that's as many satellites fit into the fairing, and you want to use up as much space as possible. But let's just set a fairly wide prior. So we'll say that we think it's a mean of 50. We think before seeing any information that the intercept is centered at 50, but could vary normally could vary as Gaussian distribution with a standard deviation, all that jazz. And then we'll use the mu. We'll set mu. And so you don't have to do this in PyMC3. You can just multiply the parameters directly and do the regression directly. But this has a benefit, which I will talk about in just 1 second. Stat count dash relative launch day plus beta 0. So what happens here is we can actually leave this out and model this like this. I'll put a comment here. You don't need the pm.deterministic. So you don't need the pm.deterministic, but if you do this, what happens is you create a node in the backend, in the Acera backend. So previously the backend was called Theano, but we've forked it and now it's called Acera, and we're making a bunch of changes to it. But essentially, the backend will keep track of mu and what the values of mu are, rather than just discarding them. So that'll be nice. Call this y, and then we'll say pm.normal. So we'll assume that this is also distributed with some noise. Oh, I should make this a scatter plot because I want to see the noise. Okay, cool. So we'll say, well, I'll call this num satellites. Num sats in space. And we'll go with that. And then this is, oh yeah, we need one more parameter. So this is our mean estimate of any values here. I forgot our sigma. So this is our error term, equals pm dot half normal. I use a half normal. So I'll say sigma. And I'll give this a pretty wide standard deviation as well, say 30. So the reason I'm doing this, normal distributions have pretty thin tails, and if you set a small standard deviation, you're setting low probability values for things that are far in the tails. But if I set a value of 30, actually, no, it's screw it, I'll just set a value of 100. If I set a value of 100, that puts a lot of mass all the way up into like the 200, 300 range of possible errors. So we'll just do that. And because this is a pretty simple, I mean, this is a relatively simple problem for a sampler, like it should be fine. So let me just copy and paste the boilerplate. All right, so I'm gonna call this set number. Set number. Oh yeah, and I promised I'd show you what the difference is, but I didn't. So let me do that next time. Let me do that after the samplers work. Can't contain an assignment. Did you mean equals? Oh. Okay. Init got unexpected keyword sigma. Oh, SD. All right. Wrong dimensions. Oh, and I forgot my observed. Okay. I messed up a keyword, and I forgot to put in my observed values, which are stat count cumulative. All right. And we're in business. So while this is going, it should be pretty quick. PyMC3 uses a sampler called the no U-turn sampler. It's this nuts thing. And that is the fanciest gradient-based sampler on the block, as it may be right now. So this is like sort of the state of the art. People are trying to come up with new ones. Actually, people are coming up with new ones. Pretty smart folks. So this might get superseded pretty soon here, but right now it is good. It's good. It's a very efficient sampler, and efficient in both the computational and in the statistics terminology. So let's talk about what the difference is here. PyMC3 used to have this object called a multitrace that was specific to PyMC3. The problem is that every library would make their own version of a posterior, like a posterior object. So it was really hard to trade results and share results and things like that. So on the Arby's project, we have created this structured thing called the inference data object. And what it has is it has all the different bits and pieces that you want from, or you could be using during your Bayesian inference in one nice package that's consistent. So people can do their inference in like Stan or Turing or whatever they want. And then if they decide to put the results in an inference data format, then you can do all of your diagnostics and model comparison with the same format, which is pretty gosh darn handy. So this is good. There are no issues with the sampler, and would be surprised if there were, because linear regression is pretty much as easy as it gets. Let's just plot a trace just to check it all out, and looks pretty good. We'd expect our beta to be negative because looking at the regression, our intercept would be negative at 0, and then this looks pretty solid, pretty handy. 1.2. I mean, at a glance, it looks like a pretty good fit. Sigma seems suspect. I gotta admit, I'm a little. Oh, you know what it is? I know what happened. I know what happened. Oh my god, you guys, you know what happened? I didn't put the date filter in. Oh, what a mistake. So we'll say filtered sats. Okay, so let's actually go through this because this is actually pretty interesting. This is pretty suspect because it's telling me that my that we're not launching satellites very fast, which seems pretty wrong, and also that there's a lot of noise in the normal estimate around the mean, like way more than I would have thought looking at this plot. But that's because I included all the data. But you know what? For the sake of the live stream, let's plot everything, and then I'll show you what it looks like. So I'm just going to copy and paste plotting code because, I don't really want to plot this all by hand again. So here's an example of another univariate regression, and I'm just going to copy and paste all this junk. Yeah, okay. That's exactly what we want. So let's do some good old copy and paste here. Let's say set count. We want set count min, set count, set count mean. Ooh, I need these alpha and beta. Oh, that's a mistake. I gotta fix that. All right, let's just plot that for now. Let's just see if that works before we do that other stuff. Okay, that looks good. This should be set count, and this should be stats. Actually, this should be relative date. Oh, it didn't like that now. I screwed something up. Well, we don't actually need to do this, so let's just do. What did I do? Oh, I renamed my data frame. That was dumb. Okay, well, don't overwrite your objects. That's a lesson in life. All right, let's fix that. So let's name this one set count x. Set count x. Set count x. Okay. All right, we got that back. Okay, let's do these one at a time. We want to plot the observed. No, we want to plot the dependent variable. Sorry, the independent variable, which is the days. And we want to plot the number. Second cumulative. Well, I destroyed my array and I didn't fix it all. Okay, got that back. Okay, and you're starting to see the issue here. So we got that, and then let's actually plot the posterior density, because this is anyone can do this, right? This is this linear regression. A single point line estimate you can get from basically Excel or Tableau. Like, not all that impressive. But what we can do is we can plot the highest posterior density, which is, I think you really only do with Bayesian stats. Well, you can do it with frequency stats too, but Bayesian stats make it nicer. Logistic stat. Okay, I know what I messed up here. I call this mu. Variables named differently, so mu. Okay, here we go. So this is what we have. This is why things are messed up, and having this this density plot is kind of a nicety as well. Having this highest posterior density. So what we have here is we have the mean posterior line if we model this whole thing together, even these far out points. But clearly, it's not a very good line, as Neil had pointed out earlier. This really looks like it needs a log transform. But the nice thing, at least property-wise, is you still get an estimate, but you get these wide uncertainty intervals, right, kind of back here, and you get the narrowest uncertainty interval at the middle. So not a great fit. I mean, just looking at it, obviously it's pretty terrible, but it's nice to have uncertainty fits, I guess, rather than just the mean line. But we are definitely not going to stick with this. What we want to do is get back to our filtered data. So let us go back up here. And this actually might be another good exercise. So I'm gonna keep this as a good exercise for these people that are reading a book. But we're gonna do this. We're gonna do a filtered satellite count. And I should have how I'm gonna do this. For the sake of this webcast, I'm gonna just destroy my old data frame just to make it work. It's a little late. So I'm just gonna overwrite it here. And I'm gonna rerun this regression. And don't need to look at inference data, but let's look at our trace again. And we have a bunch of divergences, so this is interesting. Divergence. Okay, so for those who don't know, divergences are telling you that that your gradient-based sampler is trying to sample a point, but it actually can't get a good estimate of the log probability of a particular area. That may be because it's not well defined, or there's tricky geometry or something like that. And so these usually mean you have sampling problems. The reason this is interesting is that for something this simple, I definitely would not be expecting divergences. It seems very off. So let's see what the parameters end up being. Let's just go with it for a little bit. Okay, so the estimate is not too bad. So it's kind of interesting that we end up with divergences. So what I'm trying to say is the fit doesn't look too bad when I plot it. And let me make this a little bit better. I'm just gonna artificially change this to 800, just because I can see it, or maybe 600. Okay, so it doesn't look terrible, but we're getting some issues. So let me see if I can diagnose this on the fly. Let's see what's going on. So what's interesting is the divergences don't seem concentrated. So sometimes you see them concentrated in one region or another. I don't see a large concentration of divergences in any one of the plots. What I think might be happening is that the beta 0 is so far negative that that we might need to set a better prior. So let me try that. I'm not 100% sure, but let me just try it. See if that helps. Any? I'm gonna guess no, because I can tell that it's already. Oh, we're already getting some stuff here. Okay, so this is pretty weird. It's pretty weird to be getting divergences at this point. So something might be wrong with my data. That's one thing to look at. That's the first thing I looked at. So let's look at stat count. And things look pretty all right. None of these are null. There's no random aberrations, so we're good there. The multiplication looks good. Oh, so another one is the standard deviation is massive. So let me try. Okay, so here's where we should do this the real way, which is setting a prior predictive distribution. So let me show you what a prior predictive distribution looks like. So what a prior predictive distribution does is it shows you what the possible fits are before there's any data. So prior predictive, I'm going to call this prior predictive equals pm.sample prior predictive. Let's see if I got that right. Oh, this actually might be a. Let me find it. Where is it? Oops. Sample prior predictive. Okay. Yeah, that's what I have. Okay. Sample prior. Okay. Sample prior predictive. That's what I got there. Do not look like it's sampled. Oh, I guess it did. So I actually need to file a bug ticket because it should tell you. So it's supposed to tell you that it's sampling the prior predictive. The fact that it didn't is a little bit concerning. So I'm gonna have to fix that. But here, what we got is we got these things called prior predictive samples, and what they do is they tell us that if we're just using our priors, which is the distributions prior to being conditioned on any data, what would possible regression fits be in this case? And I want to plot those because they're good to plot. So I'm going to again copy the some code from another notebook. Oh, can you check the prior scale? So Neil is saying check the scale in beta 1, which is the unit again is per days, but the scale is per launch. Yeah, actually Neil brings up a good point. The scale might be off, which is one issue. So let's do so if the scale's off, the prior predictive check will actually help us see that. So let's actually just plot it. So I've been lazy in these last couple examples. You should think through your priors more than what I have been doing, which is just kind of putting them down. You really should be running prior predictive checks or using informed priors. And I've just been winging it, which is not the best, and I end up with all these issues. So let this be a lesson. Think about your priors some. And so we're going to do our first prior predictive check here, which is we're going to plot. We're going to plot our draws against each other. Inference data has no attribute. Posterior. Oh no. I might have to go through all my work that I want to. Let's see if this works. Okay, a little bit better. And then we'll say x equals np dot linspace 600 to 1000. Take increments 1000. Okay, so here's what a prior predictive check says. And you can see it's pretty much a disaster. Let's just double check. Oh, something's. Yeah, actually, this is exactly what it says. So here's the issue. If I haven't scripted the plot, what's happening is, at least I think what's happening. I should double check my math. But if you set really stupid priors, you end up saying that all these lines are possible lines prior to actually fitting the data, like all of these. I guess probably that's true. So all these lines are possible lines, and this is ridiculous. Like, we would never have something that starts up this high or starts down this low. Like, this is crazy. This could be one reason I'm getting issues. This actually goes right into the comment that Neil had, which is are my scales off? And yeah, my scales could also be off. So what we want to do is I'm going to do a couple things. I'm going to center the regression, which means the intercept of the mean will go through 0. That'll just make it a little bit easier for the intercept parameter, which actually ideally should be 0, but and then that should just let us focus just on the slope. So we're going to say, let's do a little bit more data cleaning here. Okay, so we're going to say stat count dash actually I'm gonna change this to 0. So instead of doing centering, I'm just gonna shift. So I'm gonna say relative launch day minus relative launch day dot min. Well, oh man, that's what happens when you don't do that right. Okay, let's reset this. Sat count, relative launch day. Plot this, looks good. Good there. Okay, so what we did now is we set a relative launch day to 0. So on day 0, we don't actually need on day 0, we don't actually have any satellites in the air. This actually means we can get rid of the intercept parameter altogether. So this is an interesting thing, because we're starting a regression at 0, 0, and we know that on the 0th day, well, actually, we need a little bit of a regression. I'm sorry. So we can set this. We can actually set this to a fixed number, and I'll probably come back and change this later. But we can set this to a fixed number because we know on the 0th day there were 2 satellites. We don't have to estimate that intercept whatsoever. So we can just set this to a fixed parameter of 2, and that just lets us estimate the slope and the sigma, and that should be fine. There's no rule that you have to model everything. So let us just do that. Let's see if we get any divergences. And this actually is much better. This is great. So now we can plot our trace again, and things are looking a little bit better. I'm a little curious about the beta. It seems off, but oh no! To Neil's point again, the scale. I keep forgetting about that. We're modeling this in days. We're not modeling this in how should we call it? In launches. So to Neil's point, we have a different scale of our input than we would normally. So and I need to so I need to fix this. So I still have these 2 in here, which I don't want, but I don't have them up here, so I think I just messed up on my plotting. So let me just double check. Relative launch day. Okay, that looks good. We're going to start this at 0. We'll go to max. Where are things going wrong? So this is the not fun part of, this is actually the part that I always dislike, is I gotta go through all this. So this is an interesting result, but I'm trying to figure out why I'm still getting the Still getting those other values in there. Oh, they're in there. That's because I didn't filter them out. Of course. I'm sorry. I took the filter out. That was not even me. So sat count equals. Let's just do it up here, just to double check. Okay, this should filter out the earlier data points. And we can just, it looks like it has. Unfortunately, I have to recalculate the early date again. Okay, there we go. So I'll set the relative launch date to the first one here, and I know I'm sort of butchering this regression now, but I set the relative launch date to the first satellite launched after our filtered stuff. So now if I plot this, same thing. Just plot it down here. It starts at 0 and then it goes up. So we can say from the first day, every day, how many satellites are being launched. So to go to Neil's point again, it's not the number of launches that's the x-axis. It's the scale is the number of days. We'll run this regression once more. It's looking good. Plot a trace. Things are looking solid. Our estimates of the mean are nice, and you can tell they're getting a little bit more dispersed as we move out, which makes sense. I don't need that. We'll plot this. All right, that's looking pretty good. What is setting my very long x-axis? Well, I don't know, but let me just do the easy thing. ax.set xlim 0 400. All right, not bad. So I'd fix the slope, the intercept. So let's actually unconstrain that. Let's actually go back and get rid of that. So let's actually put that back in. Let the intercept float. So I could set it to 60. I could set it to 60 because we know that. But let's just let the regression, do its thing. Since we know it's 60 per launch, we can set this to 60, and then give this a pretty small, pretty wide standard deviation, 30, and we'll leave all these parameters the same. Oh, I need to fix this. I'll have to run that again. Okay, 1 divergence, that's not terrible. 2 divergences. Usually if you get 1 or 2, it's not the worst. So I'm just gonna count them as false positives. They're over here. Actually, this is fine. They're over here in a low density region of the posterior, so it makes some sense why those might occur. I'm not sweating it, so let's just take a look at a regression, and it's looking pretty good. I have to figure out which one of these is screwing up the scale, but let's just set this things manually for now. YLM to 1000. Well, I definitely, oops, 100. That's too low. All right, okay. I'm not gonna complain about that. That looks pretty good. Let's just look at our parameter estimates and make sure they check out with reality. Just because I'm curious. And we'll just stick here. And yeah, this is good. So, so this is a fun fact. interesting. Okay. Maybe I filtered out one extra data point, maybe one more than I need to. I need to figure that out. But I think the interesting part I have, Elon wants to get, he wants to get 10,000 satellites up there, which means he'll take, at the current rate of 2 a day on average, it's going to take a long time. It's going to take, 5,000 days. So it's like 13 years before Starlink is all good to go. So SpaceX is definitely going to have to speed up their daily average of launches. Now they're planning on doing that, and it's part of the plan. But they're really going to have to pick up the pace to get to Starlink numbers that they want to get to. So that's cool. With that's all I got. I mean, these are the 2 examples I needed. I needed one logistic regression example, and we got it. I actually think this one's pretty good with the rockets, both daily and number, and then we got one with Starlink. So this is gonna be pretty good for the book that we got here. I mean, if I might selfishly promote this thing, there's just a lot of. I'm excited to get it out just so I don't have to write it every day. Because every day I wake up and I'm like, I gotta write this stupid book. But it's like a marathon, right? You gotta do it. Let me show the table of contents though, because it's pretty cool. So, I don't know. We got like things that we covered. Well, we got the basics. So what is Bayesian methods and all that crap. They got linear models, which is we were doing this chapter, but then there's other chapters on splines and time series and additive regression trees and ABC and all that. So, at some point I gotta write exercises for all of this stuff, and I'll probably be back on streaming talking about it, and hopefully joined by you folks again. Tyler asked, what's the ETA for the book? I'm going to say we forecasted Feb. We're definitely way off. I think I'm hoping in the next couple of months. So I'm going to type in the chat. Hoping for a draft for a publisher-ready copy. But that's what we really want to get it out there. But we're over the hump. I think it's nearly almost there. Most of the chapters are written out. Let me skip. My favorite chapter is the BART chapter. But a lot of the chapters have stuff written and there's a ton of content. We're just writing the exercises and cleaning up the figures and the code, and then it's got to get copy edited, which means that the CSG Press is going to read over it and fix any things. But hope to get it out soon here. Thanks for asking, Tyler. And then meanwhile, if you got Bayesian questions, just feel free to ask. I mean, you got me and a whole bunch of others that can help try and answer for you. But hope to get this singular thing out for you. But otherwise, thanks, guys. This was fun. I think I'm going to do it again. Tyler and Niels, thank you so much for your engagement and your questions and sticking through. It really gives me hope that more people will join next time and people will find value in this. All right. Enjoy your evenings, folks. I'll see you around.